Hey Dr. Zhang, so this is our first fluids video project and we're going to verify the theory of surface tension. So to do that, I have a rubber band and I got some water and we're going to see if the surface tension that is holding the rubber band up is going to be greater than the weight pushing it down or equal to it so that the rubber band will float. So let's test it out. I'm going to take this rubber band and I'm going to set it down very carefully so as to not have extra force acting on it. That wasn't very good, but as you can see, the rubber band does indeed float. So if the rubber band floats, that means that the surface tension is equal to the weight pushing it down, so the rubber band is not going anywhere, it's in equilibrium. So let's look at the math to prove that this does work. Okay, so right here I have 5 of the same size rubber bands all piled onto each other, and the scale is showing 5 grams. So we're going to say that each rubber band is 1 gram, and that's what we're going to use in our calculations to verify. So let's take a look at the math for this surface tension. So the formula for surface tension is sigma, which is the surface tension constant, times the length of where the water is touching the surface of your object. So the surface tension constant at 25 degrees Celsius, which the water was measured as, is 0.072 newtons per meter. And the length, which I measured by cutting the rubber band in half, is 0.18 meters on both sides. Now, if we look at the free body diagram, we can see that the weight is pushing down on the rubber band and the surface tension is pushing up, so they have to be set equal to each other. So now, let's do the math. We know that the force of the surface tension, we have to multiply the length times 2 because the water is pushing up on both sides of the rubber band, not just one. So we do sigma times L times 2 equals mass times gravity. The mass is measured to be at 1 gram, which is 0.001 kilograms. We do the math, and we find out that the force of the surface tension is actually greater than the weight. And that makes sense because a rubber band floated. If weight was heavier, then it wouldn't float, it would sink. So the calculations show that this comes out to be correct. Now there are other variables such as when I dropped the rubber band into the water, it wasn't a very clean drop and may have added some more downforce. That downforce could have forced it to go under more than it should have and gotten more wet. But fortunately I was able to drop it a little slowly so it didn't do that. So those are some of the variables that could have hindered our experiment. So I got the opportunity to verify this.